So today we'll talk about sparsity based regularization, which is really a hot topic in machine learning techniques. I will be with you. I'm Shadi Al-Barkoni. I'm PhD candidate and chair for computer aided medical procedure CAM in Technischen Universität München, Munich, Germany. So generally speaking, if you would like to take this example number one from a medical environment, so if we have a bunch of people, bunch of patients, and we would like to have their blood test, so we have in this case n number in samples, and we would like to investigate their genes behavior for each sample, so we have n number of genes. So we can build up the matrix A, which has m rows, which is the number of samples, and the n columns, number of genes. For instance, A11 belongs to the patient number 1 and his gene number 1. And we have the y vector for each patient, if he has a disease or not. In this case, we can make a linear combination between, we can just a times x equal y, and these x are the parameters. In this case, our goal to learn the classifier to predict the disease, if he has a disease or not, for future observation. On the other hand, these x parameters, we can know from those x parameters which genes are responsible for the disease. We can also take another example number 2, also from medical application. If we have a patient and we would like just to take an X-ray for this patient, so we assume we have a latent variable X, and just insert the patient with this CT scan. So this CT scan or an X-ray has it's a medical imaging system which has a matrix A and can be modeled either a nice model or a blurring or a projection matrix. And we have an output which is the observation or the measured values Y. We can also implement, or we can just formulate the linear relationship, and we can say A times X equal Y, and we can add some noise which can be modeled as a Gaussian noise. So this goal to find the solution for the latent variable X. All of these problems actually can be solved statistically. We can just solve for maximum likelihood, and solve for the probability of Y given X, which can be assumed as a Gaussian distribution which has AX as mean and there is some variance. Or analytically, we can solve for the ordinary least square error, minimizing the norm 2 of X minus Y, the error term. So the solution can be formed as a closed form solution. This is the predicted X equal A transpose times A inverse A times A transpose Y. But actually in a real life the problem is not like that. The problem, it's more difficult, so we have to check the poseness and fitting, and actually we have to think carefully about this stuff. Let's go to example number 2 and let's just check for this stuff for A transpose A matrix. We have to check if it's an overdetermined, so we have many solutions, or if it's underdetermined, so maybe we don't have any solution, or we have infinite number of solutions, and we have to check if it's singular matrix or non-singular. So we have zeros, singular values in this A transpose A, so it cannot be inverted. And also we have to check if it's ill-conditioned, well-conditioned, which when we have some near zero singular values, and if it's ill-pose or will-pose problem. On the other hand, for example number 1, also we have to select these X parameters carefully, to avoid underfitting or overfitting. That's why we have to select them carefully to find the optimum values or optimum parameters to achieve the minimum error. In this case, for example, we have these two curves. The first one for the training data, when we have the small error, which has a nice curve. But for these testing data, when we use this testing data, so we have this error. That's why we have to select these parameters carefully to find the minimum error. For both cases, we need regularization to penalize for this problem. So we have to add prior information, either from statistical point of view to solve for maximum a posterior, or adding some penalty constraints to the least square error. So in this case, we have ridge regression using L2 penalty. Also, for this problem, we have a closed form solution, and we can just add this lambda I for these singular values, and we can solve the problem. If we would like to have a look to a geometrical interpretation for this problem or for these L2, if we have a system just in two-dimensional, and we have system matrix A and this observation Y, and just we would like to draw the distribution of the E norm, which has a Gaussian distribution in this case. So, and it's distributed along this principal component analysis of the matrix A. So, adding the norm, and there is a solution here in the middle of this distribution. So, usually when we add, let's just have this point and just projected on the 3D coordinates. So here are the points on the curve of the distribution of the E norm, and we have this x1 and x2 curves, x1, x2 plane, and this is the E direction. Here we have A times x1, on the other hand we have A times x2, and the summation of those two vectors would be ax. And we have the observation y vector, and the difference between y minus ax would be the error norm, which is drawn in yellow color. So if we add the norm 2, which is a circle, so we actually shrink these ax into this circle. If we increase x1 and x2, so we just increase these x1, x2, or we increase the lambda parameter until touching the curve of the E distribution to find the minimum error. So we have to compensate between those data term and this regularizer term. And this, for instance, we got this point as a solution when those curves touch together. But this is for a non-singular or for non-singular matrix. If we use a singular matrix A, so the distribution would be prolongated along one direction as a line. So in this case, just if you increase x, we can just end up with a solution here in this point. But if we use the L1 norm, which has like a diamond shape, so we actually make the solution more sparser. In this case, we just get rid of from x1 and just we have solution in x2. That leads us to define the sparsity, or why we need the sparsity. So besides a good prediction for these x parameters, actually we need the most discriminative information in the data. On the other hand, if we gathered redundant set of measurements, so we'd like just to have a data-driven selection scheme. Moreover, sparsing the solution that leads us to make a compression and just get a small number of parameters to describe the model. here comes a question, which is really a good question: how the selection of the P norm can affect on the solution. So let's just have a visualization of the P norm in 3 dimensions. If we have 3 parameters, in this case, if P equal 4, we have like a round cube. If P equal 2, L2 norm, so we have the sphere. If P equal 1, L1 norm, we have this diamond. And if P between 0 and 1, so we have this non-convex shape. So if P goes to 0, we end up with a non-convex problem, which is really complicated and it's a little bit difficult to solve, and the solution would be sparser. If P goes to infinity, we end up with a convex problem, can't be solved, but we over smooth the solution. At the end, I would like to thank actually our chair for computer-aided medical procedure to give me the chance to join this amazing chair and to contact those expert guys either in machine learning, reconstruction stuff. And at the end, actually, I just would like to say life is too short to learn machine learning. At the end, if you would like to have some real medical application just depicts the effect of P norms, just contact me. It's my pleasure just to have your feedback regarding this lecture. I hope that you enjoyed this small lecture. Here is my LinkedIn account and my home page, and just drop me an email if you're interested to see more medical imaging application. Thanks for your attention.